Welcome back to Operating Systems Crashcast. I'm Victor, and today we're diving into Section 3.5, Examples of IPC Systems. Sheila, are you ready to explore some real-world inter-process communication implementations?
Absolutely, Victor. It's always exciting to see how theoretical concepts are applied in practice. Let's start with POSIX shared memory. Can you give us an overview?
Certainly. POSIX. Shared memory is a method of IPC that allows multiple processes to access the same memory region. Imagine it like a shared whiteboard in an office where different teams can write and read information.
That's a great analogy, Victor. How does it work in practice?
Well, processes can create or open a shared memory segment using specific system calls. Once attached, they can read from or write to this segment as if it were part of their own address space. It's fast and efficient, especially for large amounts of data.
I see. Are there any drawbacks to using shared memory?
Good question. While it's fast, shared memory requires careful synchronization to prevent data corruption. It's like multiple people writing on that whiteboard simultaneously. You need rules to avoid conflicts.
That makes sense. Now, let's move on to mark message passing. This is quite different from shared memory, isn't it?
Absolutely. Mac, which influenced modern operating systems like macOS, uses a message passing system for IPC. Think of it as a postal service for processes. Each process has a mailbox or port where it can receive messages from other processes.
Interesting. How does this compare to shared memory in terms of functionality?
Well, message passing is more structured. It allows processes to send discrete messages, which can include both data and typified information. This is great for client-server architectures and distributed systems. However, it can be slower than shared memory for large data transfers.
I can see how that structure could be beneficial. Are there any unique features of Mac's implementation?
Yes, Mac introduces the concept of port rights, which control access to ports. Think of it like having different keys for different mailboxes. This adds a layer of security and flexibility. Also, Mac's message passing is location transparent, meaning it works the same way whether processes are on the same machine or across a network.
That's quite powerful. Now, let's talk about Windows IPC. How does Microsoft approach inter-process communication?
Windows actually provides a variety of IPC mechanisms, combining aspects of both shared memory and message passing. For instance, it offers shared memory through memory-mapped files and message passing through mechanisms like pipes and mail slots.
That sounds quite versatile. How does this compare to the POSIX and Mac approaches we've discussed?
Windows aims to provide a flexible toolkit for developers. Its approach allows for both high-performance local IPC using shared memory and structured communication using message passing techniques. This versatility is particularly useful in enterprise environments where Windows is prevalent, as it lets developers choose the best tool for their specific needs.
Thanks for that overview, Victor. As we wrap up, could you summarize the key takeaways from our discussion on IPC systems?
Certainly. We've seen 3 different approaches to IPC. POSIX shared memory, which is fast but requires careful synchronization. Mark message passing, which offers structured, location-transparent communication. And Windows IPC, which provides a versatile toolkit combining aspects of both. Each has its strengths and is suited to different use cases.
Excellent summary, Victor. To conclude our episode, I'd like to remind our listeners that understanding these IPC systems is crucial for designing efficient and secure multi-process applications. Thanks for tuning in to Operating Systems Crashcast.